Welcome back to our third lecture on test of hypothesis. And here we're going to look at the case where we have two more than two populations. Okay. So we are considering test of means. Of course, as I said, we can do test of proportions and so forth, but we will come back to those later on. Okay, so now we are going to talk about the case where we have more than two populations. And for the test of means, it is usually referred to as the analysis of variance. Okay, all right. So these are things we have done in our other courses on statistical methods. So we are now going to see how we can do this in R. Okay. Now, so in here, you have more than two populations, and we want to check whether the means are the same. Okay. So for example, we get back to our anorexia data, okay, and this data, remember, we said it is in the mass package, and I can display them again. So you see that the treatments that were administered were three, right? We have the control group, the the CBT group, and then the family treatment. Okay. So here, if first of all, before I enroll the people, I weigh them, okay, the pre-weight. I now want to check, are their weight significantly different? Okay, their average weight, are they significantly different? That's what, in this case, we have three groups, so that's why we are going to use analysis of variance. So here, the null hypothesis will be that H naught is that whether mu1 is equal to mu2 is equal to mu3. Because if we have more than three populations, we can still use the same thing. Any k number of populations, we can use it, okay? So how are we going to perform this analysis of variance in R? Well, there are several ways you can do so, but one of the popular functions for doing so is called AOV. And I'll use AOV because it comes in handy, because just after that, you see, we know that for analysis of variance, it will tell us whether there are differences between the groups. If there are no differences, we will not reject the null hypothesis. If there are differences, which means we have rejected a null hypothesis, the test ends there. It won't not tell us which group is different from the other. Now, if I want to do this, like if I want to check which particular group is different from the other, then I must go in and do what we call a post hoc. Now, such a post hoc test, I will have to test them one after the other, like one. So we revert back to the t-test, right, where we consider two populations at a go. Now, it is easier when you use the AOV to pass this through any of the um, um, post hoc tests like the PK test to easily find which observations are, sorry, which groups are different. Okay. So the AOV needs a formula and it needs a data. Those are the two main arguments I'm going to use to perform our test. Okay. So here, as I said, my aim is to check whether the pre-weight populations are different. In other words, those that are assigned control group to CBT group, they are different. So how do I do this? Well, I must first input in the data, and the data is what? Anorexia, okay? And this anorexia, my formula is that I want pre-weight, right? Pre-weight as a function on my treatment, which is 3. What is this? It's just that remember the box plot when we wanted to plot like observations on each particular group. So it's the same thing. So I regress, and remember an ANOVA is a linear model. So what is happening is that I regress my pre-weight on my treatment, okay, in this data anorexia. Okay, so there it is. Okay, but so this is my results. But in order to get a complete results, we usually will so let me say pre weight ANOVA. Let me say pre-weight ANOVA. So we must give it a name, right? A name of our model. And then after that, I'm going to get the results. I use summary. So I get summary of my results. And of course, it is the model that I have fitted. I want a summary of it like this. Okay. And there it is. Okay. So this is a result. Remember, you may remember this as what? An ANOVA table. Okay. Now, remember that for an ANOVA table, we have treatment, you see, which is in this case, a coincident, we have treatment, but that's what we've been using, okay? And then you have residuals. Of course, the total, I will not give you the total because it's quite easy to see that for degrees of freedom, you add the degrees of freedom for the treatment plus the residuals, and that should give you n minus 1, where n is a total number of observations. Sum of squares will add them to get the total sum of squares, and the mean square, we get our f value, and then the probability, the p-value, okay? So now that's our results for this. And how do I interpret my results? Okay, so first of all, I can use the p-value, which is quite an easy way to describe your test or interpret your text. What is the criteria? Well, we say that if the p-value is less than the alpha, okay, which is our level of significance, we reject the null hypothesis. Now look at the p-value is 0.552. Of course, our confidence, level will be 0.05. So if you look at this, what do? We will fail to reject the null hypothesis. So what it means is that there's no significant difference between the treatment groups, okay, for the pre-weight. It means the groupings, there's no significant difference between their averages, okay? All right. Now, if we have to use the F to conclude, then I need the quanta, or I need to read my F value from tables, just like a statistical table. But as I said, we can do so in R, right, by using, in this case, QF, okay, which is the quanta of the F distribution. Our P should be 0.95. We need our DF1, which is equal to 2, okay? Look at over here, that's the treatment group. DF2 is equal to 69. Okay. If you want to know what this is, you can go to QF. I will briefly talk about probability distribution right after this video and post it for you so that you'll be conversant with it. Lower the tail is true. Okay, so this, yeah, so that's enough for us to note our KF. Okay, so it's 3.12. So if you want to read this, you must take an F distribution table, okay, for 0.05, okay, and then you read degrees of freedom 1 at 2, and then with 69, you get 3.12. Okay, now if you come back to your table, you see, your F value is 0.59. And remember, for F, our criteria or our critical region is this. So if we were to, so critical region, as we do in the hypothesis that you say, we would have said that is this. So we would have said that reject H naught if F is greater than what? F, of course, F calculated. Which is the F that we calculated from our sample. And in this case, we will say that since F, sorry, I should do it the other way around. The F you calculated is greater than your F. And in this case, this is F from what? From tables. From tables. Okay. From the F table. The F tables. Okay. So and this from F tables, if I should F tables, let me do it here. It means we'll read F 0.05 at 2 and then what 69. That's what you would have read from the F tables. Okay. So if this is greater than that, what do we mean? And since F so from our results, we will say that since F calculated, which is equal to 0. What? 59999 is less than F, which is equal to is less than F is less than F 0.09, which is equal to 3.13. What is our decision? We reject. No, we fail to reject. Yeah, we fail to reject H naught, and conclude that there is no significant differences between the average weights pre-weights of the participants in the anorexia experiment, something like that. So that's how you will conclude this test from your tables. Okay, that's it. Okay, so that's the first part. Okay, now so let me go back and give some comments. So here, what were we doing? We check for test for equality of average pre-weights. Test for equality of average pre-weights of the participants in the anorexia data. Okay, so that's all we wanted to do. And here we say read the critical value from F tables. And that's what we have done. Okay. Now, the next thing I want to do is that I want us to now test for equality of average weights for the post weights of the anorexia patients. Okay. Now, so here I will do the same test, but now my interest is in the post weight, right? So I'll go here and copy this, okay, and paste. Okay, and then I'll change pre to post. So instead of pre-weight, it will be post. But of course, the data is the same, anorexia. Okay. So first of all, I do this, and then I see post. Okay. So there it is. We have this. So now how do you interpret this? Look at the p-value at first. The p-value is very small. So here they work with our conclusion. There is some significant differences between the average post weight of the anorexia patient. Why is it so? Because the p-value is less than what? Alpha, which is 0.05. Okay. Now, there's also significant cause. This only gives you, you see, there are 3 stars over here. So what R is telling you is that this will be not, there will be no significant differences only when you set your alpha to be equal to 0. Okay, but that's 100%, so it doesn't make sense in that case. Okay, now if you want to use F to be able to do it, remember our F was 3.12 or 3.13. So here you see, since F computed from our sample is greater than what? F that we read from tables, we will reject the null hypothesis, right, of equality between the variances. So our conclusion here is also that there exists significant differences between what the average post weight of the of the patients, okay, in this experiment. Okay, so you see the first one, there were no significant differences. The second one, which is the post weight, there exist significant differences. What this test fails to tell us is what are the groups, or which group is different from the other. Okay. Now, in order to do so, we need to perform a further test. Okay. And that test, we call it post hoc test. Post hoc test. Now, for such test, so the post hoc test will help us determine which groups are different from each other. Okay. Now, so the idea is you only go in for this test when you have rejected your null hypothesis, or when there is a significant difference between your groups. Then you want to see which groups are different. Okay. Now, so the post hoc test, what we will use is 2K. 2K honest significant test. Okay. So let's look at it. Okay. So it computes 2K's honest significant differences. We say it creates a set of confidence intervals on differences between means of the levels of a factor with a specified family-wise probability of coverage. The intervals are based on studentized range statistics, 2K's honest, and so forth. Okay, so essentially look at X. X is a fitted model, usually an AOV fit. And remember, our post ANOVA is an AOV fit statistic. So we can put in, remember the confidence level is set at 0.95. If you are doing your test at 0.90, then it means you must come in and change this to 0.90. So we are going to use the 2K HSD, and we'll use just the first statistic. So I just copy this, and then I paste here, and then I'll say my X is equal to what? My post XOD. Now we cannot use a pre-weight. Why is this so? Because the pre-weight, we did not reject the null hypothesis. So there's no need. If they say there's no differences between them, why do you force yourself to check for differences and so forth? So that's it. Okay. Now, so how do we interpret this test? Well, you look at it, the result is this. It says 2K's multiple comparison of means. 95% family-wise confidence level. So this one is going to take each, group and compare it with the other group. So the first one is a treatment. That's the treatment we are doing. So it compares control with CBT. The average difference is negative. What does this mean? It means the post weight of the CBT group is what? Greater than that of the control. All right. So once this is negative, what it means is that the average weight of those people in the CBT group is larger than that of the control group. Okay? Okay. Now, if you look at this is a lower and upper confidence interval. So what it means is that this interval encloses 0. Okay? So the interpretation is this: although CBT group, they have the weights are different, the average weights are different, and CBT is larger than that of, or they weigh more than those in the control group. The difference is not significant. Why is this so? Because the interval encloses 0. So you cannot rule out equality. Equality will be when their weights are the same, right? The average weights are the same. So in other words, there is no significant differences between the control group and the CBT group. Now, if you want to use the p-value to look at it at 0.005 level of significance, our p-value is greater than that. So when we say our criteria is reject H naught if what? The p-value is less than the alpha. In this case, the p-value is what? Greater than the alpha. So we fail to reject H naught. So whether you use the confidence interval or the p-value, you essentially come to the same conclusion. Next one is the family treatment and the CBT. The difference is positive. So what it means is that family treatment records, averages that are higher in terms of number or larger than that of what? CBT. Okay. Now the difference, the lower limit is this, and then the upper limit is that. Okay. Now, if you look at this, what is it? The p-value is also large. So we may say that there is no significant difference between the family treatment and CBT. But of course, we can say that family treatment generally requires what? The weights are more than that of what? The CBT group. Okay. Just that it is not statistically significant. Now look at the last one, which is family treatment and control. The difference is positive, the difference between them means, which means family treatment requires larger weights than what? Than that of what? Control group. The lower limit is 3.94, the upper limit is this. So you see this one does not include 0. So this I can confidently reject the hypothesis of no difference between them. Alternatively, if you look at the p-value is quite small. So we may reject our null hypothesis of equality between family treatment and control group. So if our conclusion is that the CBT and control are not significantly different, however, family treatment is completely different from that of the control group. Okay, so if you were to recommend this, one of these for the for implementation, you will record family treatment because that seems to give what? More weight or than the rest. Okay, so that's how we conduct this ANOVA test. Okay. So now that's the first part of this ANOVA test. Okay, and the rest of it I will devote to checking the assumptions of all these tests that we have done, which is the one sample test, the two sample test, the more than two sample test. We will look at some of the assumptions and whether they are satisfied. If they are not satisfied, what kind of test can you perform? Okay, so that will lead us to non-parametric test, but I will take that later on.